Today we're talking about free fall, which in your book is section 2.5. So you can see Wile E. Coyote here demonstrating for us, and he's a great example. So I hope you've watched Looney Tunes or are paying attention to his behavior right now, especially at the beginning there where he's motionless for a second. Okay. So in our parameters here, we are going to talk about free fall as a simplified model of motion of something that is accelerating downward due to gravity alone. So we are going to, at this moment, ignore the fact that there's air resistance, because it is there. I mean, objects on planet Earth are falling in the presence of air and experiencing that force, but right now we're going to keep it simple and ignore that. And so the magnitude of acceleration that falling objects feel is given a nickname. It's given G, and here on Earth that is an average value of 9.8 or 9.80 or 9.81, okay? On the right-hand side of this slide, you can see how if we were drawing a motion diagram or one of those like breadcrumb diagrams here, you can see that as the object falls, it's speeding up. And so these are equal intervals of time. This has been labeled with the distance that it falls. I don't remember what the time intervals are here, but they've labeled the distances so that you can see that it's not falling an equal amount of distance because it is accelerating. I thought I would just put the values for G at some different locations on planet Earth so that you could compare here and think about that a little bit. And then, of course, because these values vary by what planet you're on, or, I mean, there's definitely the sun is our biggest source of acceleration due to gravity, but we will get into that in another chapter. That would be the biggest of all, right? But we can see these values are varying depending on what planet you're near. And if you Google this, we can talk about what our value of G is at our elevation or above sea level here in Milwaukee. So what we are saying here is that for objects in free fall, because we are ignoring air resistance, or basically we're saying there are some situations where air resistance is negligible or it's ignorable, then that acceleration is not depending on mass or shape of the object, okay? And so if you looked at the penny data back when we did our graphing, you saw a scatter plot that if you stack pennies up and you drop them from a certain height, then you just get no relationship between basically the mass of that stack of pennies and how long it takes them to fall 2 meters to the floor. So that's part of the explanation for why we don't see a difference. Once we talk about terminal velocity, you'll understand more behind this story here. Okay, so we are still actually going to stick with our 3 equations that we use on the AP sheet. And if we really want to get detailed about it, we should replace the x's with y's to communicate that we're talking about the vertical direction. I tend to use a negative sign in front of the 9.8 or 9.80 because I like down to be negative. Okay, so this is specifying that down is the negative direction. I had trouble with my pen there. So we're going to use negative 9.8 or negative 9.80 for the acceleration if we've defined down to be the negative direction. Sometimes it's just more convenient to say down is positive. If the thing is only falling down, like if you drop a rock off of a bridge into the water, then you could just say down is positive and all your answers will be positive. And that's pretty convenient. So that's fine. It's up to you as the problem solver which dimension you pick to be the positive direction. Here, this is again defined, all these graphs are showing with up being positive, down being negative. And so you can see like a motion diagram of something that has been thrown upward with a great velocity. That's what this long V vector stands for. And it's slowing down, so the vector, velocity vector is getting shorter and shorter. It pauses up here for that moment, just like Wile E. Coyote paused when he jumped or left the cliff. Okay, and then as it goes down, it's speeding up, and you can see that velocity vector grow in magnitude. If we look at the position versus time graph, we see that parabola because the object is going fast at first, going slow or stopping for that split second, so it has a slope of 0 at the top, coming back down, changing direction. So we have the rainbow shape for the position time graph. This is for something that is going up and coming back down to the same exact location it started at. For the velocity time graph, we have that object's instantaneous velocity when time began, when it left the person's hand. If I'm tossing something into the air, then when it leaves my hand, that's what we're talking about. That's time 0. And that's when I see it have all this velocity. Where did it get the velocity? That's another chapter, okay? So we're starting there. We're watching it slow down, slow down, slow down as it reaches the top of its motion. Then speed, turn around, right? Cross into the quadrant 4. Speed up, speed up, speed up, speed up, speed up. Okay? And then acceleration is just that negative 9.8 the entire time. Okay. When you're solving free fall problems, often it seems like they don't give you enough information. So if you want to pause the video, these are my tricks, quote unquote, for solving these problems. And a lot of them are just using the basic symmetry of those graphs. So you can pause time when the object is at its peak because you automatically know it's going to have a moment there when it has 0 velocity. You know that like that happens when exactly half the time has gone by. If we're talking about something that you tossed up into the air and then went up and came back to your hand, that is a symmetric function, and it reached its peak height at exactly half the time that it took for it to go up and come back down. So you see that kind of expressed a different way, and when I say the time it took to go up is the time it took to come back down. The absolute value of the initial velocity is equal to the absolute value of the velocity that it has when it comes back to that same initial position. So again, if we're talking about as long as you don't move your hand, when you throw it, it will come back to your hand with the same speed. Remember, speed is absolute value of velocity. Now it has changed direction. So if we're talking about velocity, maybe it started with a positive velocity and then it lands in your hand, smacks into your hand with a negative velocity. Same magnitude, different sign. Okay. And then when we're solving for if they ask you for like, how high did this soccer ball get kicked or something, then remember how high is asking for just information about when it was at its peak. So that's when it had a velocity of 0, when only half the time has gone by. Okay, but it's perfectly legitimate to use all of our equations for any moment of time. So you are allowed to just pause the problem and solve for that. Where is this? Where is this located right now at this moment t? Okay, I just think this is fascinating history, so I'm never going to test you on it, but I'm sure you've heard of Galileo Galilei. And this Italian man is partially responsible for helping us figure this out. And it was a long time ago that it happened, right? And he made the argument that if things did not feel a force of air resistance, then they would all accelerate at the same rate. And then he's more famous for trying to back up Copernicus, and that's what he got in trouble with the Catholic Church about. He was not killed for that, though. He supposedly dropped objects off of the Leaning Tower of Pisa to try to prove that, but he also used ramps and other techniques to try to show experimental evidence for his hypotheses. He had no stopwatch, right? So super interesting. When we have time, we could follow these links, but you could at home as well. Okay.